Okay, let us compute a Gaussian Fourier transform. A Gaussian Fourier transform I will consider to be the following. I will integrate dx e2 minus x squared e2 minus I k x. And k is some real number. So the question is, what is this number? The steps to do this computation is to complete a quadratic form. Quadratic form to and notice a Gaussian integral and then shift coordinates for use standard Gaussian integral. So what is the first step? The first step is to say I have x squared plus I k x, and I'm asking in what way can I complete the square. So what do I need to add here to get this form? So I need to add ik and then divide this by 2, square this, and then I need to subtract whatever I'm squaring here. So I need to subtract ik squared and divided by 2 and squared. Let's see that this works. X squared plus 2x ik over 2 plus ik over 2 squared minus ik over 2 squared. Now what this is here, just for the computation, we don't care, but later we will find this useful. So I have plus ik over 2 squared, and then minus I squared, then I have plus k squared divided by 4. So this means completing the quadratic form, and here I have something independent of x, which means that if I consider this integral I of k I of k, this integral is equals to dx e2 minus x plus ik over 2 squared, and then I can already pull out that number outside, and I have here e2 minus x squared, here I have plus, so here I will get a minus k squared over 4. Then the next step is to shift variables. So I'm already doing the d. There is a 4. So defining a to be x. For this one we cannot shift like this. So we have a complex number y, and this is a complex integral. So how does it work? We need to imagine that we have the complex plane, real of y, and then imaginary of y, and that we are having an integral actually over a path in the complex plane. So it's a complex integral, and to be sure, I could also write this integral as an integral over a path gamma dz, and then e to minus minus z squared. And the path gamma defines for me what are those values z that I'm integrating over, that I'm continuously summing over. So we have this, and this is the definition of our path. So gamma is the set of z in the complex plane such that z is of the form x plus ik over 2 for x in reals. So I can have a finite parametrization gamma of t is equals to z is equals to t plus ik path, and that's our path gamma. Okay, so how to do this integral? I have my complex plane here. Here I have a real of z. Here I have imaginary of z. This point here is ik 1/2, and this path is my gamma. The next thing to do is to say that I can extend this integral until infinity, and at infinity drop down to add 2 more integrals, gamma 1, gamma 2. So in this path we are going like this, then we will go like this, then we will go on a path that will close it, gamma 4, and here we have gamma 2 going up again, and then closing interval. So we get a contour which I will write as gamma plus gamma 1 plus gamma 4 plus gamma 2, and that's an oriented closed contour in the complex plane. So I can integrate over this contour. So I will denote it like this. Then a complex number dz, and then the function e2 minus z squared is being integrated over. So what's going on here? Well, first of all, we need to, and why I'm writing here those additions, is because this integral splits into a sum over gamma without a 1, our true gamma that we actually want to compute, plus gamma 1 dz e2 minus z squared, plus gamma 4 dz e2 minus z squared, plus gamma 2 dz e2 minus z squared. Okay, and we said that gamma of t is equals to t plus ik over 2, but gamma 4 of t, the parametrization of this curve in complex plane, is actually minus t, because this one goes backwards. And because this one is going backwards, we can write the integral gamma 4 dz e2 minus z squared. We see that this is a purely real integral. So this is going from infinity to minus infinity dt e2 minus t squared. Okay, so what is this? This is minus the integral over the real line dx e2 minus x squared, which is the standard form of the Gaussian integral. So this is pi, square root pi with a minus. Another thing is that gamma 1 and gamma 2 are at infinity. So symbolically, gamma 1 of t, the parametrization would be infinity plus the interpolation between IK over half t, and basically going down towards 0. So t from 0 to 1. But because this is at infinity, this is 0, and this is 0. So let me do this more carefully. I can define gamma 1 parameterized as maybe not an x, some position L. I cannot write this one nicely. Let me write this one position at L. So I would be writing that I have a constant alpha plus IK2 1 minus t, and t goes from 0 to 1. So let me compute gamma of t. So gamma L of t is at 0. At 0, this is L plus IK over 2. Gamma 1 of L of 1 is just simply L, which means that I have the complex plane here. And here I have real of Z. Here I have the imaginary part of Z. And basically at some point L, this is gamma 1 parameterized by L of 0. And this point is gamma 1 L parameterized at 1. Okay. And in between, I'm linearly going down. So this is gamma 1 L at some intermediate point D. Now what I can do is to write that the integral gamma that I wanted to consider in the first place, e2 minus z squared, is the sum of gamma L dz e2 minus z squared plus gamma 1 of L gamma 1 of L dz e2 minus z squared plus the other contours. And how does it look? It looks like this, that I have a finite contour. It's a finite rectangular contour that goes like this. Well, it didn't do well. And this contour goes from minus L to L. Now what we can show is that the limit, so this will be gamma 1 of L, and this is gamma of L, which is just a restriction of gamma. So gamma of L of t is exactly gamma of t, but there's the difference is that we restrict the domain. So L is from minus L to L, into the complex plane. So it's a path where the parameter t ranges from minus L to L, and gamma was just unrestricted. So it's clear that they converge onto each other. So now if this L is pushed towards infinity, we see that limit L to infinity integral jumping gamma 1 dz is what I defined previously as gamma 1 dz e to minus z squared. Here I need e to minus z squared, and then this one is 0. So how to compute this? So gamma 1 restricted to L is L plus ek to t at t. That's our formula. So the integral gamma 1 at L dz e to minus z squared. What is the absolute value of this one? The absolute value is larger or equal to 0. It's also smaller or equal by the triangular inequality gamma 1 of L applied to the modulus e to minus z squared. But this is just an integral over the path where this is changing. So I can integrate dt, and this ikx will go away. But e to minus z squared is e to minus modulus, so it's e to minus L squared. And this interval here that I'm integrating over, so basically this becomes a constant. So let me do it correctly. Gamma 1 of L dz e to minus L squared. And here I'm integrating 1. So when I go to the coordinates of the path, then I have just this t going from 0 to 1. So that's my finite parameterization of the gamma curve. So this is just a constant, and this constant is just fixed and small. So we have from this that gamma 1 L we have that this goes to 0 as L goes to infinity, which means that limit L to infinity of gamma 1 of L dz e to minus z squared is equals to 0, because we just push it towards the end, and then this suppresses it. That's the construction. So that's an overly careful proof of that. Good. So now we have the structure here. So verified this by the same argument is 0. And now we need to flip the sign here. And finally, we will use the residue calculus. So what we have is our contour gamma already shifted at infinity, e to minus z squared. This function doesn't have any poles. So in the closed contour, there are inside there's 0 poles. So this complex integral over a closed curve has to be 0. So you can check Cauchy's theorem, or more generally, residue calculus. Okay, So if this is 0, then this is equal to our integral that we wanted in the first place, e to minus z squared, plus 0 going down, minus square root pi, and then plus going up, and that's it. 0. So so we get that our integral of dx e to minus x, I think it was minus k half squared, is equals to square root pi as it was. Okay, so it wasn't a standard Gaussian integral, it was a complex Gaussian integral, but we managed to compute it. Okay, so the Fourier transform of the Gaussian function is computed in this case by completing the square. That's the method of completing the square, where we got this. When we rewrite the integral, we have e to minus k squared over 4. And then this integral, which we showed that this is square root of pi. The way it has to be integrated is by noticing that we have a complex path gamma. And this complex path gamma is parameterized by some t, where the position on the x-axis, so this is t1, this is t2, changes, but the imaginary part of the z number is always the same. Okay, so once we have this, I was discussing here those paths a little bit more in detail, but once we are comfortable with taking the limits towards the infinity of the paths, then the shift going down is 0, and we see that the integral becomes much simpler. Then one part of the integral is forced to be on the real line in this construction, which gives us the actual value of the integral in the end. And then we need to make sure that we can show that the limit of this contour going towards the infinite contour, that those sideways peaks, the slopes here, that they contribute 0 to the integral because it's infinitely suppressed. It's infinitely suppressed because we can consider gamma 1 restricted to L, and then the absolute value is just e to minus L squared. Okay. Okay. So that was going to 0. And then finally, there's this theorem by Cauchy that we take the complex contour at 0. Yeah, okay. So we got this, which means that I of k, which is the full integral, is square root pi, and then e to minus k squared over 4. Good. Okay.